Hello everyone, I'm Charlotte from MDPI and I will be your host for today. Welcome to the second live session of the first electronic conference on Universe. This e-conference is hosted online from the 22nd to the 28th of February 2021 and is organised by MDPI and the journal Universe. I would like to thank the conference chair, Professor Lorenzo Iorio, the conference committee and the session chairs for making this e-conference possible, along with the speakers and of course our attendees. The conference papers and presentations are available on the conference's webpage for discussion during the time of the conference and will be published in the journal Proceedings. I would like to remind everyone that this session is recorded. The recording will be made available as soon as possible and will be posted online alongside the 3 other live sessions of this e-conference. This webinar is also being live streamed on MDPI's YouTube channel, so hello to those of you watching us on there. Today's live session is chaired by Professor Gonzalo Olmo from the Department of Theoretical Physics and IFIC at the University of Valencia and CSIC. His 3 main areas of interests are black holes, cosmology, and quantum gravity. Thank you very much, Gonzalo, for chairing this session. Each presentation will be followed by a question time. So if you have any questions for the speakers, please feel free to post them in the Q&A box at the bottom of your screen. And that's about it from me. So I now hand over the mic to Gonzalo and wish everyone a nice webinar.
Thank you, Charlotte, for your introduction. So my name, as you know, is Gonzalo Olmo, and from now on I will be chairing this session on black holes. So as you all know, we are living exciting moments in the black hole physics community, thanks to recent technologies that allow us to observe different properties of compact objects, such as the gravitational waves that they emit, and the light rings of their photon spheres. But these are also exciting moments because we have analytical and numerical methods that allow us to confront those observations with current theories. And these theories range from standard general relativity to modified theories of gravity and more sophisticated approaches such as string theory, loop quantum gravity, among others. So since the field on black holes is very broad and our time is finite, we will not be able to cover all the many interesting topics that are currently explored by our community. Nonetheless, we have a selection of talks that we hope will satisfy the interests of many of you. So in particular, we have 3 invited speakers that will talk about quantum aspects of singularities in loop quantum gravity. This will be by Parampreet Singh. Then we will have another talk by Rubiera-García about regular black holes and their astrophysical signatures. And also we will have Nicolas Sanchis Gual speaking about recent results on black holes in numerical relativity. We have 2 more presentations, one on new black hole solutions in supergravity by Antonio Gallerati, and another talk on black holes immersed in nonlinear electromagnetic fields by Anna Vukulic. To conclude, we will have an invited talk by Apurva Otsa on exoplanets orbiting pulsars. And now, before introducing our first speaker, I would like to thank all of you for joining this event and also thank the journal Universe for this nice initiative and Lorenzo Iorio for coordinating all these activities and the journal.
Thanks to you, Gonzalo.
So I think it's time to welcome our first invited speaker, Param Singh. So Param, are you there?
Yes, Gonzalo. So I would first like to thank Lorenzo for organizing this conference. I think it's a wonderful idea. Probably we should continue it in the coming years. And then I will like to thank my friend Gonzalo for inviting me for this talk. What I'm going to do today is to give an overview of some of the results on the singularity resolution, which comes from loop quantum gravity, and particularly for black hole spacetimes. So let me just share my talk. So I've tried to make this talk kind of approachable, given we have a very wide-ranging audience. And I already apologize that I will be skipping many details, but most of the things are worked out in great rigor by various of my colleagues and and for last 10, 15 years. So if you have any questions, I'll be happy to answer them after the talk, or you can reach me out by email. I also already apologize that I will be missing a big part of this session because I have to teach immediately after my talk within half an hour. So I'll be leaving soon after my talk. I apologize to all my colleagues. So the title of my talk is Singularity Resolution in Loop Quantized Black Holes and the Role of Quantization Prescriptions. And the idea essentially is that I'm going to talk about how the singularities get resolved when you loop quantize black hole spacetimes, but what kind of quantization ambiguities you encounter while you are quantizing, and how we can use internal consistency and phenomenology, which we already know for black hole spacetimes, to rule out various quantization ambiguities. So the goal of this kind of project is to rule out whatever quantum theories of gravity or quantum models at the theoretical level itself without going to observations. So this is the outline of my talk. After a brief introduction of the problem of singularities, I'll mention the main results of loop quantum cosmology on singularity resolution, which guide us to understand the same problem for the black hole spacetimes. And then I will present some details of the Schwarzschild spacetime. Essentially, I'll be covering the Schwarzschild interior, casting it as an anisotropic spacetime, and then loop quantizing that spacetime, and then understanding various quantization ambiguities which can arise, and what are the different quantization prescriptions we can follow to address these quantization ambiguities. Then I will talk about what have been the pitfalls of these various quantization prescriptions over the last 10, 15 years, and a viable choice which has emerged recently, which aims to answer all of these problems. And then I will summarize with the conclusions. Okay, so we all know that even though Einstein's theory of general relativity is extremely successful in describing our universe when gravity is very weak, when the space-time curvature is very small compared to the Planck scale, we know it's not the final theory. We know there has to be a theory which supersedes this theory in which we can address the problems of Big Bang and black hole singularities. And unless we understand this theory, we cannot answer fundamental questions about what are the precise initial conditions of our universe, what was there before the Big Bang, or what happens at the end state of the gravitational collapse. These questions, these issues have been long pending, outstanding from last 85, 90 years. And the kind of fundamental questions I'm interested in this talk to convey to you, and we'll provide some answers, is whether the problem of singularities is an artifact of assuming a classical continuum differentiable space-time manifold, or this problem immediately goes away when we quantize the space-time. One of the examples of quantization of the spacetimes occurs in loop quantum gravity or other non-perturbative quantum gravity approaches, where we directly quantize the dynamical degrees of freedom of the spacetime. So we'll answer that question. It turns out that the answer to the first question is yes. And then it turns out that the spacetime indeed has some sort of an atomic structure, a discrete quantum structure. If that is the case, then we would like to understand what is the fate of Big Bang and black hole singularities. The problem is very similar to what was there around 100, 110 years ago, when we were trying to understand the atomic structure of matter. And understanding that atomic structure of matter immediately led to the resolution of Rutherford's instability of atoms when the Bohr's model of atom came out. Can a similar qualitative picture of the atomic structure of space-time be already understood with the current mathematical technologies which we have, so that we can address the issue of Big Bang and black hole singularities? Answer to this question is again emerging to be a very positive yes in last 10, 15 years, given the progress in loop quantum gravity. And then the kind of question which we are now asking is to rule out various quantization prescriptions. Why we are doing that? Because given any quantum theory, there are lots of quantization ambiguities. And my goal will be to show that depending on those quantization ambiguities, the physics of singularity resolution can change. So this leads us to the question whether different choices in quantization of space-time affect singularity resolution and the physics of space-time beyond singularities. So this will be essentially the main goal of the talk, to answer these questions and to give you a snapshot of where we are currently. to answer these questions, the first ingredient we need is non-perturbative quantum gravity. And we all know that we do not have a complete theory of non-perturbative quantum gravity yet, but I would like to convince you that we know enough as far as technology is concerned that we can quantize simple and yet non-trivial spacetimes. What are these simple and non-trivial spacetimes? These are, for example, homogeneous spacetimes like isotropic Friedman-Robertson-Walker model, Bianchi models, which are the anisotropic spacetimes, and Schwarzschild interior. These are the playgrounds for quantum gravity techniques which we can apply. They provide a very rich and non-trivial setting because we can already start answering lots of questions which are of immense physical importance. And the interesting thing is that even though these are homogeneous spacetimes and these are anisotropic spacetimes, because of BKL conjecture, we know that the approach to generic space like singularities, the local evolution is approximated by Bianchi models. So even though we may be missing certain quantitative details of how singularity resolution may occur or may not occur, the qualitative picture these models provide can be extremely useful to understand the role of quantum gravity in singularity resolution. So I like to call this as a kindergarten of quantum gravity. This is like the kindergarten of the first grade in the school of quantum gravity. We have to learn a lot, but it still provides us lots of important lessons. And we have been using these lessons in development of various techniques in loop quantum cosmology. First of all, it gives us an opportunity to do a rigorous construction of mathematically and physically consistent model quantum spacetimes. For example, a lot of mathematical progress has been made in non-perturbative quantum gravity. But how does that mathematical progress translate to quantizing simple quantum spacetimes? These are simple yet very rich non-trivial quantum spacetimes. They are not easy to quantize, but they still give us an opportunity to overcome various challenges which we see in full quantum gravity. The second thing is one can develop and rigorously test different tools to extract reliable physics. One example of this is in last 5 years, my group has been working on extracting these physical predictions using high performance computing, which are going to play a very important role in extracting predictions in quantum gravity. These tools cannot be developed unless we have simpler models, simpler spacetimes like black hole spacetimes or cosmological spacetimes to test various techniques. So this is a very nice playground to test various tools. And finally, these models are directly relevant for observations. Whether they are observations in CMB or whether they are observation for gravitational waves, we can extract physical predictions and rule out various quantizations using phenomenology as well as internal consistency. My talk will be more relying on the internal consistency of the theory to rule out various quantization prescriptions. So let me just give you a very brief snapshot of loop quantum gravity and loop quantum cosmology. The main message is that it's a non-perturbative, background-independent canonical quantization based on Ashtaker-Barbero variables, which essentially cast gravity as a kinematical at a kinematical level very similar to any gauge theory. The main variables are the connection, the matrix-valued connection A, and the conjugate triad. The connection A essentially captures the information about the extrinsic curvature, and the triad captures the information about the spatial metric. The theory has a very high mathematical precision thanks to the work of many people in 90s and early of the previous decade. And at a kinematical level, the main message is that the classical differential geometry of GR is replaced by a quantum discrete geometry. This quantum discrete geometry is not put in by hand like various other approaches, but this is essentially derived from the theory. Now, these ideas of the loop quantum gravity were applied to cosmological spacetimes in early 2000. And there were seminal papers written by Martin Boyewald and Ashtaker, Martin Boyewald and Lewandowski, where one symmetry reduces these connections and triads using the spacetime symmetries at the classical level, and then one quantizes. So the idea is take the structure of loop quantum gravity, use the underlying spacetime symmetries of the cosmological and the black hole spacetimes, symmetry reduce the problem, and then use the technology of loop quantum gravity to quantize. And various kinematical features which we understood in loop quantum gravity, it turned out that they can be easily exported to loop quantum cosmology. Now, based on these works, there was a rigorous quantization which was performed for some of the cosmological spacetimes. And the immediate result was that it led to a singularity resolution due to non-perturbative effects. The underlying reason was that there is a discrete quantum geometry which leads to a discrete quantum evolution, which results in a bound on the spacetime curvature, which results in spacetime singularities being resolved. And these results have in the last decade been generalized to various isotropic and isotropic models, and also gaudy spacetimes, which include inhomogeneities. So these results are not only valid for homogeneous spacetimes now, but also in presence of certain kinds of inhomogeneities. And various groups have worked on these results. A nice feature which we found in loop quantum cosmology is when we study different quantization prescriptions, because given a classical Hamiltonian constraint, you can quantize it in slightly different ways. And this was essentially the work which was being done by Martin Boyewald at that time. And the question we were asking was whether different quantization prescriptions lead to similar physics, or whether we can rule out some of these quantization prescriptions. With my friend Alex Corici, I understood this question from aspects of that there should be an independence of the theory from the underlying mathematical artifacts. One of those mathematical artifacts is an infrared regulator, which you have to introduce to define certain symplectic structures. And we found that if you ask the independence from this infrared regulator, then it restricts many possible regularizations, almost all possible regularizations, and it only leaves one unique choice, which was a choice which was already introduced in 2006. It's also called as the improved dynamics, or it's called as a standard loop quantum cosmology now. We would see that this choice of infrared regulator and the physics being independent of this infrared regulator also plays an important role in the loop quantization of black hole spacetimes. But let me just give you a snapshot of the main result, which comes from loop quantum cosmology, which is also relevant for the black hole spacetimes, which is captured in this picture, where one is plotting the wave function of the universe in volume of the universe, which represents the cube of the scale factor, and a scalar field, which represents time. So what happens is that you take a state somewhere far away from the Planck scale, which is peaked on the classical trajectory. You evolve that state backwards in time, and then one finds that in the classical theory or in the Wheeler-DeWitt theory, that state will immediately go into the Big Bang. But what one finds in loop quantum cosmology is that because of the discreteness of quantum geometry, there is a bound on the space-time curvature, which results in the resolution of the Big Bang singularity, and it causes a bounce. A very nice feature of this dynamics, this is a very complicated, this picture at that time in 2006, 2007, took us like about a month to produce, running on the best computers at that time. But the nice thing is that this picture can be interpreted in terms of an effective space-time description, which has been tested extremely well using high performance computing by my group in last 5-6 years. And one finds that you can actually write down very precise modifications to the Friedman dynamics or to the classical dynamics, which capture the singularity resolution in great detail. Using this effective space-time description, we have shown that for various isotropic and anisotropic spacetimes, there is a generic resolution of all strong curvature singularities, which give us a big hope that maybe the same result holds for the black hole spacetimes. So this was essentially an introduction to the main idea of loop quantum gravity and loop quantum cosmology in very brief, and how its discrete quantum geometry leads to singularity resolution. So now I would move to the black hole spacetimes using the same technology. And a very nice thing about the Schwarzschild black holes is that if you look at the interior of the Schwarzschild black hole, it essentially mimics an anisotropic spacetime. You can take a homogeneous slicing, and then you can write the vacuum spacetime inside as a Minkowski-Sachs spacetime. The spatial manifold is R cross S2 with a fiducial metric, which looks like this. And once you have this fiducial metric, you can introduce a symplectic structure. But to introduce a symplectic structure, we notice that since we have a R here in this spatial manifold as R cross S2, S2 is compact, but R is non-compact, you have to introduce an infrared regulator to define various integrations. This infrared regulator should not matter, like in any path integral. It can be taken away in the end, and the physics should be consistent. It should not depend on this regulator. But as it will turn out, if one doesn't take this infrared regulator carefully into account, then the internal consistency would and will rule out the quantization prescription. So using the space-time symmetries, the Archdegler-Barbero connection and the triad can be expanded in this way. I'm sorry to give these ugly expressions, but they are useful to understand a very small point. The point is that you can write down this matrix valued connection in terms of two connection variables, C and B, which are written here. They here taus are the polyspin matrices, and x, theta, phi are the coordinates of the fiducial metric. Here L naught inverse is the infrared regulator. Similarly, the triad can be expanded as PC and PB, which are the components of the symmetry reduced components of the triad. And again, one finds this infrared regulator. Now, if we demand that the physics should be consistent with this infrared regulator, then the first thing is to ask that, suppose if I rescale this infrared regulator, how do things change? So under the rescaling of L naught by some alpha L naught, one finds that the connection C and PB, they rescale in the following way, but PC and B, they remain invariant. And the important thing is that in whatever quantum physics we want to write down for this space-time, physics must be independent of this freedom. Most importantly, the curvature scale at the bounds, where the singularity resolution is supposed to occur, that should not depend on this choice of the regulator. So let me just write down the space-time metric to connect to the conventional Schwarzschild metric. So the space-time metric in terms of the symmetry-reduced triads takes this particular form, where n is the lapse, and one can relate it to the Schwarzschild metric, the components of the Schwarzschild metric like this, with 2m by t minus 1, where t is the coordinate inside the Schwarzschild black hole. The horizon is identified at PB equal to 0 and at PC equal to 4m square. When PB takes the value 0 and PC takes the value 4m square, there is a horizon. The inner singularity, the classical singularity, is when both PB and PC become 0. The classical Hamiltonian constraint is the one which we start from, has this particular form where there are these triads, E's and E, these two E's, the FAB, which represents the field strength of the connections, and this omega, which captures the intrinsic curvature term. We may take the main idea from loop quantum gravity that this FAB is expressed in terms of the holonomies of the connection, like in any gauge invariant theory, the holonomies of the connection over loops, which are considered in this spatial manifold. These loops are considered in the x theta, x phi, and theta phi planes. And the edge lengths of these loops are important to be understood in the way that these edge lengths of the loops along the x direction and along S2 are parameterized by fractional lengths, delta C and delta B. And these fractional lengths are constrained by the underlying quantum geometry. So how do the quantization ambiguities arise? I can start with this classical Hamiltonian constraint, and you can start with the same constraint, but we can decide to take different kind of loops in these planes, x theta, x phi, and x theta phi planes. We can also take similar kind of loops in these planes, but then assign their areas of these loops in different ways as compatible to the underlying quantum geometry. Since we do not have a full theory of quantum gravity yet, we do not have a guiding principle from the full theory how to take these areas. But we can use certain knowledge, which we already have from cosmological models, for example, to how to assign these particular areas. So this is the cause of an ambiguity. One cause of an ambiguity can be you start from a slightly different Hamiltonian constraint. The second cause of ambiguity can be how you take the areas of the loops. And different quantization prescriptions I'm going to talk about actually differ in how you take the different areas of these different loops. Okay, and how these loops are assigned to quantum geometry. So in the quantization, which is a very rigorous exercise, and I'm just giving you a snapshot of some details. If you look at the holonomies of the connection and you write down FAB, the field strength of the connection in terms of these holonomies, one finds that there are terms like sine delta B by B delta B and sine delta C by delta C in the quantum Hamiltonian constraint. In the classical Hamiltonian constraint, these sine terms are not present. There is only B or C. this B gets converted to sine delta B by delta B, or C gets converted to sine delta C by delta C. And departures from classical theory occur when delta B and delta C are large. You can also immediately see why there is a singularity resolution. Because in the classical theory, if you look at the singularity, B and C both diverge, and therefore the Hamiltonian blows up. But in the quantum theory, because of these trigonometric factors, there cannot be no divergence of B and C, because as soon as one hits delta B to certain value, then this sign term just causes a change in the sign in the dynamical evolution, and there is a bounce. Physical consistency requires that the departures from the classical theory should only occur in the Planck regime and not when the space-time curvature is very small. And that can be only guaranteed when delta B and delta C terms are independent of L0. If they are dependent on L0, there will be fake Planck scale effects. If one is not careful with underlying construction, one would start finding very spurious kind of quantum gravitational effects, but these will be spurious because you can get those effects just by rescaling of the infrared regulator L0. So early attempts on this exercise were made by Astrophysical and Leonardo Modesto around in 2005. What they did was to take a very similar approach which was there in earlier loop quantum cosmology, and they took the fractional lengths to be constant, delta B equal to delta C equal to constant. It led a non-singular quantum difference equation, but that is not enough. One has to look at the physics of that non-singular evolution. And one found that if one looks at the space-time curvature at which singularity resolution occurs, that space-time curvature is completely arbitrary because it is tied. The physics was tied to the infrared cell, and that was not independent of it. Near the horizon, one obtained classical GR, which is a good news, so which means that one obtained the right infrared limit. But the space-time after the bounce resulted in a white hole space-time, mass of which was completely arbitrary. So in these approaches, the singularity resolution occurred at arbitrary scale, and the mass of the white hole beyond the singularity also was completely arbitrary. It could be changed just by rescaling the infrared regulator. Then there was another attempt which was made by Christian Romer and Kevin van der Sloot in 2007, 2008. It was very much inspired from the success in loop quantum cosmology, which was getting established at that time. There, these sine delta C terms and sine delta B terms, they did not suffer from any of such fiducial mathematical artifacts or the infrared regulator. That was a brilliant news for this model. But the problem of this model was that at the horizon, there was a breakdown of the model, and there were very large Planck scale effects. Also, the singularity resolution in this model was very peculiar, very different from what was seen in the earlier models. There was a singularity resolution, but there was no white hole space-time after the singularity. It was actually a charged Nariai space-time with a very large emergent Planckian cosmological constant. So the space-time beyond the singularity turned out to be very, very different from what was seen in the previous quantization. Then there was another quantization. I'm sorry to use my name, but this is the convention in the literature now. So for the current studies here, which I'm discussing. So what I did with my collaborator Alex Corici was to show that if one refines the previous works, which were done by Ashtekar and Boyewald, one can actually use the quantum geometry in a consistent way to assign the minimum areas of the loops to constant values, and the physics does not depend on the infrared regulator. We found that there are no fake Planck scale effects near the horizon, and the bounce results in a white hole space-time. But what we found was that if you start from some mass of the black hole space-time, the mass on the other side of the singularity turns out to be extremely large. It did not match the previous black hole. There is nothing wrong with the conservation here, but it was just a very, very odd feature. Then it was also found some years later that if one looks at the value of the Kreshman scalar or the curvature invariance at the bounce, then they decrease slowly as the mass increases, which means that if you're looking at astrophysical black holes, then the singularity resolution can occur at very, very small curvature invariance. Then we also found that one can refine this prescription, this Corici-Singh prescription, by adjusting these fractional lengths in certain way that there can be a symmetric bounce and these problems with curvature invariants can be alleviated. And this is what was a motivation and inspiration for the work which I did with Rubiera-García and Javier Olmedo a couple of years back, where we understood a very important feature of the Ricci-based prescription and its cousins, in the sense that if you look at the effective space-time description of these models, there is always a bounce, and therefore there is always a transition surface from the black hole to white hole spacetimes. The main insight which we used was that instead of using quantum geometry at certain ad hoc time, if one uses the quantum geometry to fix the areas of the loop on the transition surface, then many of the problems can be resolved. With this construction, we found that the fractional lengths delta B and delta C are given in this particular way, where m is the mass of the black hole and delta is some coefficients of the order 1 times LP, which is a Planck length. In this approach, we found that there is a symmetric bounce. You start from the black hole, there is a singularity. That singularity gets avoided because of loop quantum gravity effects, and then there is a white hole, and there is a symmetric mass. Like whatever ADM mass you start from, you end up with the same ADM mass on the other side. And the nice thing is that you can also extend this quantization beyond the horizon to the exterior of the region, which was also done for the first time. Let us look at some of the features of this. So in this figure, I'm comparing the way the bounce occurs. I'm plotting versus time, which is one of the, I'm taking this time as proportional to exponential of the small t in the interior of the metric. I'm plotting the Boehmer-van der Sloot scheme, which is given in this curve, and the AOS prescription, which I gave with García and Olmedo, which is plotted in this particular curve here. The classic, this is the classical theory, and this is the AOS. So this is the classical theory. This is the AOS prescription, and this is the Ricci-based prescription here. So one finds that in the classical theory, as the time will run back, you will find that PC will go to 0 eventually, and there will be a singularity, the central singularity. In the Boehmer-van der Sloot prescription, there will be a bounce, and then the universe will not become, the space-time will not become macroscopic on the other side, but will continue to become smaller and eventually reach a stable but very small value near the Planck area. And if one interprets this in an effective description, if the effective description is true at that level, then one finds that there is a charge Neri space-time on this side. In the CS prescription, the bounce is asymmetric, whereas in the AOS prescription, the bounce is symmetric. So the only difference between the AOS and CS prescription is that whether the mass is symmetric across a bounce or not. So the nice thing is that unlike the CS prescription, one finds that the curvature invariants are bounded above and have a maximum value at the transition surface, which turns out to be independent of the black hole mass. So here, for example, I have plotted the Kreshman scalar versus the time, and one finds that this turns out to be a universal bound for all the black holes, which have masses much larger compared to the Planck mass. So essentially what happens is that unlike the previous quantization prescriptions, the main message is that if one uses the prescription where the quantum geometry is used at the transition surface to assign the areas of the loops, then one finds that the bounce is symmetric and there are universal bounds on the curvature invariants. So let me just summarize the talk, and then I will welcome any questions. The main point is that non-perturbative quantum gravity effects from loop quantization play a very important role in singularity resolution in cosmological and black hole spacetimes. As in any quantum theory, there are several ambiguities in quantization of spacetime and loop quantum gravity and cosmology. The main challenge, because we do not have the observational data which can rule out these various studies, is to use internal consistency and whatever phenomenology or physical implications we can use to rule out as many quantization prescriptions as possible. This was possible in loop quantum cosmology to find a unique choice, ruling out various quantization prescriptions. And this has been the exercise in the last various years for the black hole spacetimes. In this AOS prescription, which I presented, which is based on the validity of the effective dynamics, it provides a consistent model of a non-singular Schwarzschild spacetime. It is free from various problems which have been plaguing various other quantization prescriptions. And it gives us various insights on how we can use quantum geometry on the transition surface. The explicit form of quantum difference equation is still to be worked out. So that is a caveat of this study. So this is not a full quantization. This is based on the effective spacetime description. We still do not know whether this model agrees with the effective dynamics. No one has performed high performance computations on this, but there have been very encouraging studies that for extremely large masses, at least in the Ricci-Singh scheme, there is one gets a stable evolution and one gets the signature of a bounce. So the hope is that the same would probably hold for this new prescription because it's very similar. It's very close to the CS scheme. There are still lots of open questions. This is just the Schwarzschild interior. What happens in other spacetimes? What happens if you include matter, which leads to gravitational collapse? Do the quantization prescriptions change? How do we quantize this? We are still working on those things. And there are several groups who are working on these problems and several interesting papers which are coming out. So I will conclude my talk now. And if there are any questions, I welcome them.
Thanks, Param, for your nice talk, for this summary on the progress made in loop quantum gravity. We are running out of time, but we have a couple of questions. I don't know if you can check them in the questions and answers section here at the bottom of the site.
Okay, so maybe I can try to answer Jakub's question because I do not understand. Like the loop quantum cosmology results in, one way to answer that question is that loop quantum cosmology results in a modified Friedman equation, which has a quadratic dependence. And when you are at very small energy densities and at large volumes, you recover the classical Friedman equation. One can also start from the quantum difference equation and take the large volume limit, and then one gets the Wheeler-DeWitt equation. So it gives these two examples clearly show that there is a very nice infrared limit, and loop quantum cosmology indeed leads to GR, as many papers have shown. So if Jakub has further questions on this, I'm happy to answer.
Okay. Thanks, Param, again for participating, for your nice talk, and we hope to keep reading your works very soon on these topics. So,
Gonzalo, sorry, Param, I have just a minute. I have a little question.
Sure.
Maybe I'm missing something, but what about the quantization in the case of a Kerr metric? Are there studies on that? I imagine that is clearly more difficult than with the Schwarzschild metric.
Lorenzo, that's an excellent question, and I wish like I could answer it positively. But as you say, like it's a very complicated problem because I do not know of any homogeneous slicing one can do of the interior for the Kerr metric. The Schwarzschild metric as such a homogeneous slicing exists, and one can then use the technology of loop quantum cosmology to easily quantize those slicings. So there is a lot of work which is being done to understand, for example, Lemaitre-Tolman-Bondi model and other midi superspace spacetimes, where now we are understanding how to include inhomogeneous slicings and how to quantize. So I think perhaps in 2 years or 3 years, we will have answers for the Kerr spacetime. But my hope is that the singularity resolution would hold as there is evidence from gaudy spacetimes.
Okay.
So, Gonzalo, I'm sorry, Lorenzo, please continue.
Are you working, how to say, to any order in the spin parameter, or one tries by assuming not so big values for the spin parameter of the Kerr metric?
I think the simple, right now, I am not aware of any work which has tackled Kerr metric for arbitrary spin parameters, even the ongoing works which are not there on arXiv yet. But the simplest would be to first start with this most symmetric setting and then analyze. But my belief is that if we can do for some spin parameters, it should be generalizable to the spin parameters. But the role of these kind of ambiguities will be much more difficult and richer to understand there. So it's a pending question.
Okay, thank you.
Okay, thanks, Param, again. So it is time to start the second talk. And so, Diego, are you there?
Hey there.
Okay.
Okay, so hello everyone. So so as an author, a referee, and sometimes editor of this journal, so I welcome this great idea of starting doing kind of meetings online, because in these difficult times where everything seems to be remote. So let us hope that we are able to see each other again in person. But in the meantime, so this is what we have. So today, the idea of this talk that I'm going to present today is to join two different things. So two different tricky questions, actually. The first one, in this sense, I welcome the previous talk by Param about talking a bit about singularities, because this is what my first talk, part of my talk is going to be about, is a specific proposal for the resolution of singularities in some specific models that we'll be discussing here, and trying to make a link with the potential astrophysical signatures that we could expect from these models where singularities are resolved, and how we can take advantage of the present and future opportunities that we will have in astrophysics. So because the talk is just 25 minutes, so I have skipped most of the technical details, and I will try to show you what is my reasoning about the singularities, how they can be resolved, and how from there we can go to astrophysical applications. So talking about conceptually about what we have nowadays, so we have plenty of data supporting the idea that black holes are real objects, and that they are, if they are not described by general relativity, they pretty much look like that, in the sense that general relativity predictions for the properties of black holes do match observations from different sources, from electromagnetic radiation, via different processes, with gravitational wave observations, and so on. So it's good to start this talk by having a glance to what general relativity tells us about black holes, and where the difficulties arise as far as we understand gravitational physics. So general relativity, the prediction is very clear. There is only, as far as we know, one axisymmetric solution of the Einstein equations, describing objects that have mass, angular momentum, and charge. Though the later can be usually neglected in astrophysical environments. This is no hard theorem. And so because of this, black holes are pretty much simple objects from a mathematical point of view, which allow us to extract predictions from the theory and then compare with observations, as we are doing right now in this with the array of observations that we have right now. Now, these observations have to do with the physics that happens outside the event horizon, obviously, because inside we cannot have a look unless we cross the horizon ourselves. But if general relativity describes correctly the exterior part, so it's natural to think that it's also described correctly the inner part of the inside the event horizon. And what happens when we go to the innermost region of a black hole? So one immediately sees that there is something weird occurring on this region, as described by general relativity. And this is better illustrated by having a look at the Schwarzschild solution. So this is pretty very well known. It's a very simple mathematical structure. And then one sees right away that there seems to be any kind of problem with the definition of this line element. There are two potential places where some components of the line element can diverge. One of them is not really a problem, as we learned in a process that took almost 50 years from from the finding of the by Schwarzschild of his solution until it was clearly understood, one of these divergences just signaled that we are using not suitable line element to describe non-suitable system of coordinates to describe the line element, and this apparent divergence can be made go away if we choose another system of coordinates, and then the interpretation of this divergence at when the radius is equal to 2 times the mass is just maybe a signal of the presence of event horizon, and there is nothing wrong in our description of the space-time. The problem lies when you go down all the way into r equal to 0, where there is not any change of coordinates that allows you to remove this divergence in the line element. This can be checked by computing any curvature scalar, in particular the Kretschmann, which is whose exact expression is given here, and as you can see, so this goes to infinity as you approach the center of the solution. So a curvature divergence happens in both the Schwarzschild and Weisner-Rosen solution. In the case of the Kerr or Kerr-Lehmann solution, so this curvature divergence occurs on a ring-like structure. Okay, so this is very well known in any textbook, but this problem was most clearly formulated by the now celebrated singularity theorems by Penrose, Hawking, and others at the end of the 60s, telling us that the emergence of singularities in general relativity is unavoidable. In order to prove this result, what Penrose and others did was to study a reliable criteria in order to test whether a space-time is pathological or not, which is to rely on the trajectories of free-falling observers, in other words, time-line geodesics, or the null geodesics, which are associated to the light rays and the transmission of information. Because these are the trajectories that physical observers and light rays will follow in our pure space-time, so it seems very reasonable to impose that in any well-behaved space-time, so geodesics should be complete. And then they go on to formulate a number of theorems based on 3 different conditions, which are pretty reasonable. There are different formulations of the theorems, but all of them use these 3 different sets of conditions, which are a condition on the behavior of the frequency of geodesics, which is related to energy conditions in general relativity, the existence of a tap surface if we are dealing with black holes, and the existence of Cauchy hypersurface in order to formulate the initial data problem. So these 3 conditions are really reasonable, and the theorems tell us that if they hold, then the development of geodesic incompleteness in our space-time is unavoidable. Now, this tells you that singularities are unavoidable in general relativity. They occur inside black holes and also in the early universe. And because of this, despite the observational success of general relativity, predictability and determinism are seriously threatened. So this is something that we must deal with if we want to understand how to go beyond the theory. And in turn, this has become the starting point around which many different attempts to extend the theory has taken place. So actually, right now, almost everybody agrees that general relativity should be extended in some way or another, but almost everybody disagrees on how to do this thing. So because of this, there are a lot of different proposals in the literature, from fundamental ones like string theory, loop quantum gravity, and many others, more effective formulations, and so on. So there are, you can choose your favorite theory and type it in Inspires, and you will find plenty of papers studying different properties of them. Now, because we are in the era where gravitation and multi-messenger astronomy has been born, so we have now have a big machinery in order to test the observational viability of all these proposals. So a simple example, the discovery in 2017 of the merge of a black hole with a neutron star, and the fact that the propagation of gravitational waves in the system is equal to the speed of light to a large degree of approximation. So this has been a killing machine for many modifications of gravity. And the Bachelor's bill, and you can see here from this paper of Ezquiaga and Zumalacárregui, so has been very important, with many different theories suffering heavily and requiring extra modifications in order to become viable with this. And in a few years, a few decades, we should have much more data in order to keep testing our favorite theories of gravity. So this is a heavy constraint on how to extend the theory. It comes from observational sources. So when you decide to extend the theory, one has to be very careful about what you do with the status of general relativity. So there is a trend in the literature that instead of relying on particular ways of quantizing the theory, this approach is much more agnostic about the source of the modification of gravity, and instead goes back to the geometrical elements upon which the theory is built. And in particular, the main character of this plot is a fine connection that is well known. So the fine connection can be split in general in 3 different pieces associated to curvature, torsion, and non-metricity. Now, when we formulate general relativity, we are used to think that only curvature is present. We remove torsion and non-metricity, and then we do our gravitational physics on top of that. Now, it is known since not so long ago that it's possible to formulate general relativity switching off instead of torsion and non-metricity. You can switch off curvature and non-metricity and keep torsion, or switch off curvature and torsion and keep non-metricity. And these 3 different formulations of the theory turn out to be completely equivalent. They predict exactly the same phenomenology. So this is true when you take the lowest scalar action in order to define your theory, but this is not so when you go beyond that lowest order action. So there are different, depending on whether you switch off one component, one of these pieces or another, so you will have a different playground to extend your theory. And in particular, the one that we choose is that to keep metric and the fine connection to be independent, which in practical terms means that in general you will have no metricity. Torsion can also be incorporated, but however, for the sake of this talk, I will ignore torsion. I will just assume that metric and connection are independent entities. So in general, you will have no metricity present. And in order to see if the models built this way produce solutions which avoid the singularities, so I will use 4 different criteria that I have highlighted here. And then I will go one by one to check whether my specific solutions do satisfy all these criteria for physical plausibility of the solutions. So the family of theories that we usually consider, we dub it Ricci-based gravities, basically because they are built upon contractions of the metric with the symmetric part of the Ricci tensor. So the technical aspects are described here in the caveats and below in these slides. So this particular formalism includes quite a large array of different theories. Besides general relativity itself, it includes the Palatini version of FR, quadratic gravity, Boring-Feld-inspired theories of gravity, and so on. A good property of these family of theories is that they admit an Einstein representation. So this look like general relativity with an Einstein tensor on the left and some modifications to the momentum tensor on the right. And the key point here is that everything that appears here on the right-hand side of these equations can be shown to be a function of the energy momentum tensor of the matter fields. So in practical terms, it looks like a kind of modified energy momentum tensor. On the left, what you have is the Einstein tensor of a new metric, has been introduced in these expressions here, related to space-time metric via some kind of matrix that is can be always expressed on cell as a function of the momentum tensor of the matter fields. So this is basically Einstein equations with a modified momentum tensor on the right-hand side for this effective metric Q. And once you solve this problem for the effective metric Q, you can invert this expression in order to obtain the space-time metric of the particular problem you are considering. And also, this representation shows that the field equations of this theory are second order, they are gauss-free, and they are, for many of these theories, they turn out to be also compatible with solar system tests and with gravitational wave observations carried out so far. Another good property of these theories is that there are many exact solutions that are possible to be obtained, and in particular, black hole solutions, at least in the static case, which is the case I'm going to analyze next. So there are many different, as I was telling you, so this family of theories we have been exploring quite a number of them and studying the conditions, studying whether they are regular or singular or according to the different criteria that I was introducing here. So in order to test whether the obtained solutions are geodesically complete or not, so we go to the general geodesic equation for a spherical symmetric spacetime and particularize it for the typical structure of a solution in an RBG theory, which is written here. And in the particular case of radial null geodesics, which are those that are incomplete in the case of the Schwarzschild and Dresden-Norton solutions. So you can integrate for the affine parameter via this expression, and everything on the regularity of this solution will reduce to the behavior of this new function that appears here, to this omega-1 of x. So depending on this function, you will have a singular or regular solution regarding the completeness of geodesics. So when you analyze different theories of the RBG type, you discover that there are basically two different mechanisms for the completeness of geodesics. In the first one, the central region is pushed to the future or past boundary of the manifold in such a way that the null radial geodesic will take an infinite time to get there. So the space-time is geodesically complete because there is the affine parameter of a null radial geodesics can be indefinitely extended, which is the criterion for geodesic completeness. And the same will happen for any other kind of geodesics. In the second kind of mechanism, so the center of the central of the object can be reached in finite affine time. But as you can see in the plot on the right, so this doesn't prevent the geodesic from being extended across this point to the other asymptotic region. The problem with the second case is that because there are physical extended observers that can reach the central region in finite time, and because in this central region the curvature in general is divergent, so one could wonder what will happen to a geodesically complete observer that encounters a curvature divergence on its path. In order to analyze whether this corresponds to a singular behavior or not, so we go to the usual description of the impact of tidal forces via divergences of curvature upon physical observers. In this approach, what you do is to model a standard observer as in terms of a congruence, which means that you model each particle making up the observer to be described by geodesics. So you have a bunch of geodesics describing the body, and the existence of tidal forces will disrupt the individual trajectories with the obvious danger that there could be, you could go to a situation where the volume invariance that is defined this way, which is also canonical, and whether this volume invariant describing the standard observer will go to zero. This is actually what happens in the Schwarzschild case, where you have a spaghettization of the body and the volume goes to zero as you get to the central region of the Schwarzschild black hole. And this is called a crashing tight singularity, or strong singularity that destroys physical observers. Now, when you go, you repeat the same analysis to these objects, you discover that you encounter a kind of situation where the volume invariant goes to infinity, but has not a proper interpretation within the standard law of the analysis of tidal forces within this approach. So instead of keeping this way, what we did was to use a more physical or more sensible approach, which is to get this congruence of geodesics and taking to any pair of geodesics of the body, start sending light rays on a round trip from one part of the body to another, and gauge what is the time of flight for any of these photons and whether these photons could be in causal contact all the time as you approach the complete divergence region to see whether physical interactions that sustain the body could be effectively transmitted. And we discovered that this is the case. So there seems to be no problem with the causal behavior of the internal part of the body. And according to this approach, the potential the existence of curvature divergences do not necessarily destroy physical observers. The third criteria is that is to use the fact that the singularity theorems, they deal with geodesic completeness, but by the principle of general covariance, observers with any kind of other motion, in particular accelerated motion, should also have complete paths. So it wouldn't make little sense to call a regular space-time which is geodesically complete, but that contains incomplete curves corresponding to accelerated observers with a bound acceleration. So this scenario has to be discarded by analysis of the always favorable space-time. And when you generalize the geodesic motion to the cases of acceleration, so the standard geodesic equation picks up a new term related to acceleration of the observer. And when you apply this to specific models, for instance, to the quadratic gravity model with R squared and R mu corrections, so you discover that this equation is complete in all cases, no matter what is the acceleration of the body, provided that this acceleration is bounded in all cases. So accelerated observers in these spacetimes can be also indefinitely extended, so they are also regular. I also adding that you can also study the problem of propagation of a scalar wave in this spacetime, compute using standard procedures the transmission and reflection coefficient, and you discover that there are no apparent pathologies. So as far as these four criteria is concerned, so these spacetimes that appear in these papers are regular. This doesn't mean that there could be further pathologies that we didn't cover in this analysis that could exist in this model. As far as our analysis covered regarding these four criteria, so we discovered specific examples of singularity-free space-time in these Ricci-based gravities. Okay, so far so good, but this one criticism that you could use here is the fact that you are using static charge models, but real black holes in the universe to rotate. This is a scenario we didn't consider it yet, and then we need to extend this mathematical idealized black hole to the case of the axially symmetric scenarios. Now, if you try to solve by direct attack the RBG field equations, so you discover that this is extremely difficult. And this is a very typical problem of modified theories of gravity. So we devised a different approach that we call it the mapping method that appears here in this 11 reference, which works by establishing a mapping between a given RBG theory coupled to some sets of matter fields with general relativity coupled to another set of matter fields described by a different Lagrangian density. And it turns out that it's possible to obtain solutions of general relativity of Ricci-based gravity coupled to some matter fields out of general relativity coupled to other Lagrangian density matter via purely algebraic transformations without any need to solve differential equations. So this is a very useful shortcut that allows you in particular to obtain exact axisymmetric solutions. So one example appears here corresponding to the Einstein-inspired Bonifeld gravity. And it looks like some kind of small modification of the Kerr-Newman solution in general relativity via epsilon corrections that depend on the energy density of the electromagnetic field. And with this line element, you can start doing physics of interest for astrophysics, in particular gravitational waves, echoes, shadows, and the like. And a particularly interested case of this approach is to look for qualitatively different discrimination with respect to general relativity predictions. What does this mean? Most of the modifications of general relativity canonical solutions actually introduce very small modifications with respect to them. So this is very difficult via astrophysics to distinguish whether any potential discrepancy is due to a lack of knowledge of all the details that play a role in the astrophysics description, or whether there is modified gravity effects present. So in order to discriminate between these two different scenarios, so a good idea is to look for something which is qualitatively different. So a prediction of modified gravity that do not appear in the case of general relativity. A very well-known case of this is what is called the echoes. This means that if instead of a black hole you have a very compact object but without horizon, in the process of merger, in addition to the standard trail of gravitational wave radiation, you will have a periodic release of additional gravitational waves due to modes trapped in the effective potential barrier between the surface of the object and the photosphere of the object. Another signal another new signal of physics beyond general relativity will also be the observation of double light rings. These double light rings emerge in this kind of asymmetric objects having two different photon spheres in such a way that photons passing above one maximum of the effective potential but below the other maximum will give rise to a second light ring that will appear in the spherical symmetric case that I am depicting here. And so there are specific models that are capable to produce this, and in particular asymmetric thin cell wormholes built in Palatini for gravity with standard matter energy sources satisfying energy conditions. Okay, so because I'm running out of time, so just the four messages to take home is that space-time singularities can be used as a starting point in order to look for physics, for new physics beyond that of general relativity. And new guiding principles can be obtained if you reconsider the role that we usually give to the different geometric elements that are built in upon our gravitational theories, in particular, the new freedoms that are encoded in the affine connections that we usually neglect, in the sense that we usually neglect torsion and non-metricity. If you reconsider this, then you have more freedom to play with these structures beyond general relativity. If, in particular, if you take non-metricity and formulate it using Ricci-based gravity, you discover that you can resolve space-time singularity in different scenarios according to different criteria. And the next step in this research will be to make contact with observational discriminations using qualitatively different predictions of these theories as compared to those of general relativity, and in particular gravitational wave echoes and regarding gravitational radiation, gravitational wave radiation, and double shadows regarding the propagation of light in these theories. And that's it. And thank you very much for your attention.
Thank you, Diego, for your talk. So we have a question. Can you reach the questions and answers?
Let me see.
Up here. So
okay.
Read the question.
Okay. Modify equivalence system coordinate with independence specification of the gravity. Okay. Let me read it. You mentioned several times that you modify general relativity. General relativity is equivalence of systems of coordinates and background independence of measurements. Neglecting modification of the gravitational action, will you discuss how modification change general relativity transformation of the standard model, the formation invariance? Does it change the minimal coupling of fermions? Okay, so when I said that I modify general relativity, I said two different things. One is very canonical, which is I modify the action described in the theory, not the building principles, so no general covariance, not modifying the principle of equivalence, modifying the action. The second thing that we modify, as I said, is to reconsider the physical role that the different pieces of the plane connections play in your formulation of gravity. So there is nothing there is nothing preventing you this, as I tell you, So I told you, you can formulate a theory completely equivalent to general relativity using torsion alone instead of curvature. This is the parallel equivalent general relativity. So there is nothing inconsistent about that. And then when you extend the theory, not only to extend the action, but to what building blocks for the geometry you use, so you have freedom as long as the weak field limit of the theory reduces to that general relativity and its predictions. About your second point, the minimal coupling of fermions, of course, if here I'm dealing with bosons only. And when you do this, you can safely ignore torsion. If you include fermions, which in general relativity is Einstein-Cartan, so then you need to include the connection in your matter sector, and then the torsion should play a role, right? And bosons with the metric internally contracted valence. So about the boson with metric, as I said, bosons is what I'm doing here. If you include fermions, so you need the connection in the matter sector, then the torsion appears to play a role. So you have extensions of Einstein-Cartan. So in general, you have metric affine geometries with all the lot. I mean, metric, curvature, non-metricity, and torsion interacting with matter fields. So this got quickly very difficult, but it can be done. I mean, there are many words having curvature, non-metricity, and torsion in the literature, but some simplify answers in order to start phenomenology of the theory.
Okay, thank you. So is there any other question? Lorenzo, maybe you want to ask something or comment on something? No? So if not, then Diego, thanks again for participating in this conference, and I hope to see you soon. Okay.
We will. Okay, enjoy the meeting.
Thank you. So our next speaker is Nicolas Sanchis Gual. Nico, are you there?
Yes. Hi, Gonzalo.
Hi. So feel free to start whenever you are ready.
Okay, thank you. Let me share my screen. Hi, everyone. Thank you first of all, thank you very much to the organizers and especially Gonzalo for inviting me to give this talk. My name is Nicolas Sanchis Gual. I'm currently a postdoc at the University of Aveiro. I'm part of the Graph group, and I'm a member of the Virtual Collaboration. So today I will talk about black holes in numerical relativity, and in particular, I will discuss a bit some of my results regarding superradiance, gravitational waves, and also the emission of polarized photons in binary black hole mergers. So let me first briefly introduce a bit the field of numerical relativity, which is my field of research. As you know, there's a large number of areas in physics that require general relativity, GR, to correctly describe the systems under study. In particular, if we want to study compact objects, such as black holes and neutron stars, or maybe some more theoretically exotic objects, such as boson stars. The Einstein equations play a fundamental role in the analysis of the dynamics of the gravitational field. So analytic solutions have only been found when we assume simplifying symmetries. For instance, spherical symmetry for the Schwarzschild solution, axis symmetry for curve. So if we want to study more complex systems with astrophysical relevance, so binaries, for example, this cannot be done by solving the Einstein equations in an exact way. So numerical relativity aims to solve the field equations with computers using numerical approximations to obtain the dynamical evolution of the system and provide accurate gravitational wave templates from relevant astrophysical systems. So in numerical relativity, we consider a foliation of the space-time with three-dimensional spatial hypersurfaces, which are defined by a scalar function, which is the temporal coordinate. So the metric of the space-time takes this form with these functions, the three-dimensional metric, the lapse, and the shift, and we can solve the evolution equation, so we obtain the time evolution of the gravitational field in time. So I will what's the link between numerical relativity and black holes, and binary black hole in particular? So the detection of gravitational waves by LIGO, Virgo, and Suncagra are opening up a new window into the strong field regime of gravity. The data so far is well fitted by the expected physics. This is quasi-circular mergers of Kerr black holes and neutron stars. But it is interesting and important to understand if alternative scenarios involving black holes, but maybe involving also exotic compact objects, can also fit the data, or how much these are ruled out by current or future detections. So obtaining gravitational waveforms from these alternative scenarios could lead to their discovery if they exist in nature. So, for instance, if we want to obtain the gravitational waveform of a compact binary merger, we see that we have three different phases. We have first the inspiral, during which we have the quasi-circular inspiral, during which the two bodies, the two objects are getting closer due to the loss of angular momentum through the emission of gravitational waves, and the gravitational wave signal for this phase can be obtained using post-Newtonian techniques. The final part of the gravitational signal, the ring down, corresponds to the ring down when the final object has formed and it's ringing, can actually be obtained using black hole perturbation methods. But for the last several orbits, for the plunge and the merger of the two objects, to obtain this part of the gravitational wave, the peak, so we require to perform a numerical simulation using numerical relativity. And in particular, this is a bit of a historical background. The first ever evolution of an orbital merger of a binary black hole spacetime was performed by Franz Pretorius in his breakthrough paper that actually was published exactly 10 years before, in the 14th September 2005, 10 years before the first detection of gravitational wave, so GW 150914. And actually you can see here the first numerical relativity gravitational waveform from his simulation that we could call the NRGW 050914. So he performed the evolution of a binary composed of two equal mass, non-spinning black holes, through a single plunge, orbit, merger, and ring down. The final black hole, he estimated to be a Kerr black hole with angular momentum parameter A equal 0.7, which is in very good agreement with the source parameters obtained from GW 150914, which is basically the merger of two non-spinning, almost equal mass black holes. He also gave an estimate of the total energy emitted through gravitational waves to be of the order of 5% of the initial rest mass of the system, which is again in very good agreement with what was measured for GW 150914. So in 2005, so Pretorius managed to perform this first merger of two black holes through only one orbit, the plunge and the merger, and then the ring down. And nowadays we have this very long, we can perform these simulations for several orbits, and we can obtain these very long gravitational wave templates, and we can then compare to our real gravitational wave events. This in particular corresponds to the first detection, GW 150914. So you can see here that so the prediction from numerical relativity, the waveform predicted from numerical relativity, is in very good agreement with the strain detected by the gravitational wave detectors, LIGO and Virgo. And now we have catalogs with hundreds and hundreds of gravitational wave templates from binary black hole mergers, from binary black hole simulations, with several orbits, with precession, with different mass ratio, with high spin, and in a quasi-circular orbit. These again can be used to try to feed the signal and extract information from the source of the gravitational wave event. Okay, again, let's talk about numerical relativity and some of these gravitational wave events. In particular, well, almost all gravitational wave events so far are very similar to the first one, to GW150914, in the sense that it's a chirp type of signal. We have these three different phases of the signal: the in-spiral, the peak, which corresponds to the merger of the black holes, and then the ring down. So it's a chirp because the amplitude and the frequency of the wave, it's increasing with time. See here that it increases in frequency and in intensity, in amplitude. So it's a chirp, like the chirp of a bird. So it's a long signal. But then we have GW190521, which is the latest individual event reported by the collaboration. And this event is rather special because it's the most massive binary ever detected. Actually, the final mass of the black hole is 150 solar masses. So this is the first observation of an intermediate mass black hole. Moreover, it's the most massive colliding individual black holes, and the masses are actually within the pair instability supernova gap. This means that it challenged this discovery, this detection, challenged our stellar evolution models. And there's also some, it seems that there's some preference when performing a Bayesian analysis for precession. So the system seems to be precessing. So the spins are not aligned with the orbital angular momentum, but instead they are non-aligned. So the trajectories will precess, and we can see a modulation of the gravitational wave signal, of the amplitude of the gravitational wave signal. So if we look at the morphology of 190521, you can see if we compare it with the first one, for example, GW150914, that it's rather different. So you can see this is a really clear chirp type of signal within spiral, and the peak and the merger, we cannot see really much of the ring down. But for GW190521, there is no in spiral, or at least we cannot see the trail of the in-spiral. It's a rather short type of signal. It's like a burst of gravitational waves. So it could be that it's a quasi-circular binary merger, just like GW150914. Things that being the most massive event that we have observed. So this means that the frequencies of the signal are lower with respect to the GW150914. So due to the sensitivity curve, and especially to this wall, this loss of sensitivity for low frequencies. So for GW150914, we can see that we can still see a long part of the in-spiral, but for GW190521, the in-spiral could be hidden behind this low frequency wall. So if we check the signal in time domain, you see that it's a rather short signal. There is no really an in-spiral part. There is this there is no the power of the pre-merger part of the signal is very small. So this could be explained with a precessing signal, in the sense that the in-spiral part is modulated to the precessing nature of the binary. But it could be, and that in-spiral is hidden behind this wall of low frequencies. But it could be that the signal is short by itself. It's really a burst of gravitational waves. We do not have this pre-merger signal. So with some of my collaborators, with Juan Calderón Bustillo, with Tony Font and Alejandro Torres, we perform a lot of several numerical simulations of head-on collisions of spinning black holes, of Kerr black holes, and we compute the gravitational waveforms. And because we wanted to see, we tried to see if precession could mimic extreme eccentricity, in this case, head-on collision. Sorry. So you can see here that in frequency domain, you have the precessing waveform, that there is this modulation due to the precessing nature of the signal. While this is the head-on collision, where we do not have this part, the pre-merger. We only see the kind of the peak and the ring down. And due to the sensitivity curve of the gravitational wave detectors, it turns out that we can overlap a precessing signal with a head-on collision for very large masses. So we injected a head-on collision waveform into noise with some mass, with some large mass. And actually, the masses of the individual black holes for the head-on collisions are outside the Bayesian gap. But when we try to recover this signal from the noise using a precessing waveforms, precessing templates, it turns out that it can fit for large masses, the head-on collision, but the masses of the individual components are within the Bayesian gap. So it could be that GW190521 is actually a head-on collision or an eccentric merger without really a pre-merger signal, an spiral part. And when we try to feed it with a precession, we get that the individual black holes are within the Bayesian gap. So we perform a Bayesian analysis of GW190521 using these simulations of head-on collisions of black holes, but it turns out that it can be discarded. The preference is for the vanilla quasi-circular precessing binary black hole interpretation from the LBC, because the head-on collision is too short to explain the whole signal. And just very quick, I wanted to say that then we try with head-on collision of spinning Proca stars, which are vector boson stars. And actually with Proca stars, we saw that we could fit, and there was a slight preference from the Bayesian analysis, even with respect to the vanilla quasi-circular precessing binary black hole. So Proca stars could fit really well this signal. Okay, so I've been talking about mergers of black holes in GR, but then we can also study mergers of black holes in theories beyond GR. In particular, I've been studying these theories, these Einstein-Maxwell scalar models, which are like a toy model of the extended Gauss-Bonnet theories. In this case, we have GR. We have an electromagnetic field which is minimally coupled to the Einstein part, and a scalar field which is also minimally coupled to gravity. But then the scalar field is not minimally coupled to the electromagnetic field. So if we have a Rayson nostrum, electric charge black hole, we can scalarize the black hole and get a different solution in which we have a scalar hair. So we can also perform mergers of this scalarized solution by starting with two Rayson nostrum and then a perturbation of the scalar field that will scalarize the black holes before the collision. You can see here in this simulation, and then it forms a final black hole, scalarized black hole. And we can compare the resulting signal, the gravitational wave, with respect to the ones from non-scalarized solution, to Rayson nostrum or to Schwarzschild black hole solution. So you can see that the difference between them vary depending on the value of the coupling and on the charge to mass ratio. And finally, we get this signal which the pre-merger, if the collision it's right at the peak, then the pre-merger signal is different with respect to the merger of the non-scalarized solutions. Okay, so I've talked about numerical relativity, how we can compute these gravitational waveforms from binary mergers, but we can use numerical relativity as a tool to study other fundamental problems. For example, what is the endpoint of the super instability and how we can form hairy black holes. So as you know, black holes have no hair, meaning that they are well described by the Kerning family. So they are characterized with the mass, the electric charge, and the angular momentum. So if we have a Schwarzschild black hole without electric charge, without spin, if we put some cloud of bosonic field around this Schwarzschild black hole, what we get is a quasi-bound state, meaning that you form a configuration around this Schwarzschild black hole that is decaying with time, exponentially decaying. So it's not hair. What we get is what has been called a bosonic wig. So the solution is not static or stationary and will tend to a Schwarzschild black hole with more mass. But in 2014, Carlos Herdeiro and Jean Radu found that if we consider instead a rotating a Kerr black hole with angular momentum, they found a stationary and asymptotically flat solutions of the Einstein complex massive Klein-Gordon and of the Einstein complex Broca systems that were called Kerr black holes with bosonic hair. And these solutions are really stationary, they are time independent. And the bosonic field is synchronized with the rotation of the black hole, and they are both in equilibrium. So regarding the super instability and this hairy black hole, if we can define for Kerr black holes this critical frequency, which is proportional to the horizon velocity. If we take this answer for a scalar field, for example, we have three possibilities. First, it could be that the oscillation frequency is higher than this critical frequency, then the imaginary part of the frequency is negative. So we have these wigs, we have these quasi-bond states that are decaying with time into the black hole. So this is always the case for a Schwarzschild black hole because this critical frequency is 0. So this is always greater than 0. Then we can have that the oscillation frequency matches exactly this critical frequency, and therefore the imaginary part vanishes. So what we have are these Kerr black holes with bosonic hair, these equilibrium static configurations. So we need a complex bosonic field because even if the field, the real and imaginary parts are oscillating with time, the amplitude of the complex field will remain constant with time. So at the level of the stress energy tensor, it's time independent, and we can get solutions that are static or stationary. And these are these hairy black holes. So, and the third and last possibility is that the oscillation frequency is smaller than this critical frequency. In this case, the imaginary part is larger than 0, and we have exponentially growing modes. So we can trigger the super instability. This means that if we have an incident wave of bosonic field that is scattered off a rotating black hole, fulfilling this condition, then the reflective wave will have a larger amplitude than the incident wave because it will extract energy and angular momentum from the black hole, increasing its own energy and angular momentum. If we can trap these superently scattered waves by assuming a massive field or imposing some cavity around the black hole, then we can trigger what has been called the black hole bomb. And studying the endpoint of the black hole bomb has been an open issue since the 70s, because we needed numerical evolutions to reach the nonlinear regime and solve, therefore, the fully nonlinear equations. The thing is that the scalar field super instability around a rotating Kerr black hole, the time scale of the growth to reach this nonlinear regime are too long, this time scale is too large to be performed, to be studied, even with current computational capabilities. But there is a more favorable situation, which is consider instead a charged Rayleigh-Nordström black hole, so with electric charge. If we put it in a cavity in some reflecting boundary conditions for the scalar field, and we add some charged scalar field perturbation, we can trigger the analog system, which is the charged black hole bomb. In this case can be done in spherical symmetry, and the time scales are much shorter. So we can study the endpoint of the charged black hole bomb. So we did that, and we saw that there is first a phase of super-radiant growth during which the field is extracting energy and charge from the black hole, increasing its own energy. So we are here. For the Rayleigh-Nordström, we can also define this critical frequency, which is proportional to the electric potential at the horizon. So we start here, but the field will extract energy and charge from the black hole. So this electric potential will decrease, and so the critical frequency will also decrease. So we go from here to the point in which the oscillation frequency matches this critical frequency and the imaginary part just vanishes. So we reach the saturation and the equilibrium, meaning that we go from the super instability to the formation of a charged hairy black hole. You can see it here. in this evolution of the electric density, energy density of the scalar field. You see how it increases with time, but at some point we will reach the equilibrium and we form this static configuration of a charged Hairy black hole. In 2017, East and Pretorius managed to perform the rotating black hole bomb, but considering a Broca field, a vector bosonic field instead, and they found the same features. They found the superabundant growth, the saturation, and the formation of a Hairy black hole, of a Kerr black hole with Broca hair. And the solutions at the endpoint of the superabundant instability that East and Pretorius found were the same that Carlos and Eugene found as solutions, these Kerr black holes with Broca hair that they found in this case for Broca. So at the endpoint of the superabundant instability, there is the formation of these Hairy black holes, of these Kerr black holes with bosonic hair. This was found thanks to numerical relativity and numerical simulations. So, okay, so I'm getting to the final part of my talk. I will also talk about this work that I did with some collaborators about the spontaneous creation of circularly polarized photons in binary black hole mergers. So about this quantum effect in curved spacetimes, and actually in dynamical curved spacetimes. So this work was done in collaboration with Adrián del Río, Iván Agulló, and José Navarro Salas. It was published in PRL, and it's a follow-up of one result that Adrián, Iván, and Pepe found, which is that the electromagnetic duality can be broken if you consider a curved spacetime and a quantum electromagnetic field. So basically, this delta Q is the difference between the number of left-handed circularized photons and the right-handed circularized photons. So there could be a polarization, a change in the net polarization of the spacetime if this quantity, which is this invariant, which is the Kern-Potriak intensity, or if the integral is non-zero. So they started studying these analytic solutions, the Kern-Newman family and other analytic solutions, and they found that either this quantity was zero or the integral was zero. So for all the stationary and static solutions that they compute this quantity, they found that it was always zero. So they asked me and my collaborators, Basilios, Mewes, and Tony Font, if we could compute this quantity in binary black hole mergers, in these really highly dynamical situations, to see if this quantity would be non-zero during the merger and the emission of gravitational waves. So we performed these different mergers of binary black holes with a couple of orbits, one orbit, a couple of orbits. So here I show how the two black holes will merge, how the grid is changing with time to follow the two black holes. This is how we perform these mergers of black holes. And what we found is that indeed this quantity was non-zero, and it was especially really large. Well, it was large when the two black holes were close and they merged. Actually, the peak, we identified the peak of this quantity with the peak of emission of gravitational waves. So the net polarization of the spacetime changes when we have a merger of black holes, but not all black holes, because we found that for a Schwarzschild black holes or aligned Kerr black holes, this quantity was zero, so it was conserved. But in the case of precessing system or head-on collisions where the spins are not kind of aligned, then we can have this kind of behavior and these peaks. So there's an emission, a creation from the quantum vacuum of a flux of circularly polarized photons. But in any case, the number of photons is really small. So this effect is really small. It's comparable to that of the Hawking effect. So it's not something that we can really observe. Okay, so I'm going to conclude So I've tried to stress that numerical relativity is a tool, it's a really powerful tool to study black holes in GR or even in beyond GR theories. So for instance, we studied the endpoint of the super instability using numerical relativity. And in this nice paper, I think there was this synergy between gravitational waves, simulations, binary black hole mergers, and these quantum fields in curved spacetimes. And that's all. Thank you very much.
Thank you, Nico. Very nice talk, very informative. So very nice to see all the progress your field and you personally have made in the last years. There are no questions in by the public, but I'm curious about many things, but just wanted to ask you something, just in case to see if you know more about this. So you have shown that there are, in the case of these hairy black holes, when you are studying the superradiance instability, that eventually you end up with a black hole with hair in different cases. So are there numerical, analytical approximations to the final solutions? Has anybody explored the analytical approximations to be compared with your numerical results?
Yes, so as far as I know, there are no analytical solutions, but there are numerical solutions.
Yeah.
So like,
my point is just to see if one can use the numerical results somehow to build analytical approximations, just to understand, because this is the late time regime of this solution,
yes.
Right? Yes. So at some point, it seems reasonable that some approximations could be possible.
Yeah, indeed. I mean, so I think what I mean with numerical solutions, I mean, it's really, you can get like these stationary solutions. Mm-hmm. It's like obtaining a solution of boson stars. So it's not analytical because you need a numerical code to get the solutions, but it's not the result of a numerical evolution.
Yeah. Okay. Yes.
Yeah. So you get some.
You're separating the time dependence with the frequency.
Exactly.
Okay.
Yeah. So that's what Carlos and Jim found. So it's really stationary solutions that are not from the endpoint of any evolution. It's really a stationary solution that they obtain.
Understand. Okay, so is there any other questions? Someone who wants to comment? No? If not, then thank you again, Nico. It's been very nice.
Thank you very much, Gonzalo. I will.
And we are right on the schedule, a bit late, but acceptable. So our next speaker is Antonio Gallerati.
Good morning. My name is Antonio Gallerati. I'm from Polytechnic of Turin in Italy, and today I'm going to speak about new solutions, new hairy black hole solutions in a gauged supergravity framework. So I will try to be very schematic. So we will have a short introduction, very short introduction, when I will discuss this new model and the explicit solutions that we can find in this new model. And then I'm going to end with some concluding remarks. So first of all, we are mainly interested in anti-de Sitter black holes, ADS black holes. Why are we interested in this kind of black hole configuration? Well, the idea is that they are very important physical configurations because they play a relevant role in the so-called ADS-CFT conjecture. There is a correspondence, a connector correspondence between ADS supergravity theory living in a d-dimensional bulk and a related quantum field theory living in the d-1 dimensional boundary of the bulk supergravity theory. This means that we can have try to extrapolate relevant information about the strongly coupled dual gauge theory that is very difficult to very difficult to understand. But if we are able to describe the supergravity theory living in the bulk, we can extract relevant information. Second, in general, configuration is interesting apart from the interest in finding new solutions in the framework of general relativity and gravity theory. We are interested also in the thermodynamics, since these configurations possess phase structures that can undergo some kind of critical phenomena like common to other thermodynamic systems. And finally, we were also able to find the BPS black holes. There is black hole configurations preserving a certain fraction of supersymmetry, and this is important because this residual supersymmetry allows to map a computation of the entropy from the weak regime that is very difficult to handle to the strong coupling regime of the supergravity theory that has a formulation that is known, but is given in terms of the black hole solution. So we have a map between the superstring, weak regime of superstring and the strongly coupled regime of supergravity, where the formulation is known in terms of the black hole. Then, let us now discuss this new model. We are going to consider a general n=2 supergravity theory featuring a single vector multiplet and featuring the so-called phi-Opoulos terms, Fi terms. These are components of the so-called embedding tensor, that is a spurionic object that encodes all the information and the parameters of the gauging of the theory. We need a gauged theory because we want to introduce also a scalar potential so that we can have a richer structure and a more predictive theory. The schematic structure of the bosonic Lagrangian of the theory has this general form. That is, we have the Einstein-Hilbert standard Einstein-Hilbert contribution, the scalar part of the Lagrangian, and the vector part of the Lagrangian. So we start from a model with only one complex scalar that we call Z, two vector field strengths, F mu nu, and a scalar potential that is different from 0. Then we are going to deform this theory, introducing these Fi terms, encoding all the information about the gauging of the theory. Then we can now embed this black hole solution in a supergravity model. And this is important since in this supergravity framework, many physical aspects of this theory can be better understood. For example, we know that the scalar fields of the theory, if we are able to embed the black hole solution in a supergravity framework, can be characterized to use the geometry of the sigma model. There is the scalars can be seen as coordinates on a manifold. In particular, they span a manifold of the spatial scalar type. So using the geometry of this manifold, we are able to find the correct form of the scalar potential and of the properties of the scalars. Then we are going in particular to focus on a consistent truncation to the T-daton field of the theory only. That is, we are going to consider only the real part of this complex scalar, and we, imposing some conditions, we are able to consistently truncate this theory to the dilaton part only. Once we have done this, we are able to find these new explicit black hole solutions, and these solutions depend on a real parameter that we call nu, and these new solutions interpolates between different single dilaton truncation of the maximal areas of the n=8 supergravity gauged theory in 4 dimensions. We have a general n=2 theory for all the possible values of the new parameters. For special values of the new parameter, we have a consistent truncation of the maximal n=8 supergravity theory. And this is important because the standard SO8 gauged supergravity maximal theory can be uplifted to an 11-dimensional supergravity. Okay, now after the dilaton truncation, we find this final form from the Lagrangian. This is the Einstein-Hilbert term. This is the scalar part of the Lagrangian. This is the scalar kinetic term, and this is the scalar potential. Here we have the vector field strengths, and the non-minimal coupling between the vectors and the scalar field is encoded in this I matrix. Okay. So in the explicit solution, we were able to find two families of solution, one with electric charge and one with magnetic charge. And we also find the correct duality that mapped one family into the other. Then the schematic form of the solution is written here. This is the functional form of the scalar, is expressed in terms of this x variable that is the radial variable. The vector fixed strengths have a more complicated form that depends on the radial variable, on this gamma lambda that are the electric or magnetic charges, and this alpha parameter that is a parameter that controls the strength of the ionic gauging of the theory. And this is the schematic form of the metric of the solution. Okay, this eta is an integration constant, is a parameter that is an integration constant. Here we find the standard d sigma k, a two-dimensional metric that if k is equal to 0 is locally planar, if k is equal to minus 1 is locally hyperbolic, or if k is equal plus 1 is the standard two-dimensional spherical metric. Okay, this new solution are written in a particular form that makes the uncharged limit well defined. This is limit, this uncharged limit gives us the standard form that we have already, the non-standard form that we already found in a previous work. And this is particular because this new solution behaves in a way that is different from the standard literature, because the uncharged limit is not Schwarzschild or Schwarzschild IDS, but gives again an uncharged but hairy black hole solution. So is a very interesting formulation. Then now some details about the thermodynamics. After a change of a suitable change of coordinate, we find the correct boundary expansion of the scalar. That is, we are going to make a change of coordinate from x to x function of r to find the correct boundary expansion for the scalar field. And this phi 0 and phi 1 that is the coefficient of the of the r to the minus 1 and r to the minus 2 expansion of the scalar field correspond to ADS invariant boundary condition. Namely, they induce a triple trace deformation in the boundary theory. And this also tells us that the conformal boundary symmetry is preserved, so the black hole mass can be read off the asymptotic expansion of the GTT component of the metric. And okay, this is what we get. If we expand the GTT component of the metric, we are able to find the correct form from the ADN mass of the black hole. And this depends on this L is the anti-de Sitter radius, and this mu is a parameter that is written in terms of the anti-de Sitter radius and on the electric magnetic charge and on the alpha parameter. Then about the thermodynamics, the temperature and the entropy can be found using the standard formulas for a black hole. And this is the explicit result for the entropy, and this is the standard result for the temperature. And that has to be calculated for x plus, for which the fx function is 0. That is the poles of the metric. Finally, this is the explicit form from the physical charge and electric potential for the family 1, that is the electric family, and we have an analogous formula for the magnetic family. This is the family number 2. And using all the results that we have found from the thermodynamics, we can see that the first law of thermodynamics is satisfied, and this is good, okay? Since the thermodynamics tells us that the solution is correct. Then let us say something about the BPS solution. The idea is that it is possible to find BPS configuration. There is a black hole solution, black hole configuration preserving part of the original supersymmetry, and this can be done if we fix the charges Q1 and Q2 in terms of the other parameters of the theory. This is the solution again only from the electric family, and we have an analogous formula for the magnetic family. So why is this important? This formula for the charge are found imposing the vanishing of the SUSY variation, that is of the so-called Killing-Spinor equation that we have solved explicitly. If we restrict to this BPS solution, this supersymmetric black hole solutions, we can see that we have BPS black holes with the finite area of the horizon if we fix the parameters alpha in terms of the ADS radius L. All the new supersymmetric black hole configuration have a non-singular horizon, and this horizon can have a local spherical or hyperbolic or planar topology, depending on the value of k that can be 0, -1, or +1. Finally, if we again perform the same calculations that we have already done for the non-supersymmetric limits, we can again compute the thermodynamical quantities of the solution, and we can again see that the first law of the thermodynamics for this black hole configuration is satisfied using also the correct extremality condition, that is using the vanishing of the Hawking temperature of the black hole. Then finally, some concluding remarks, some other distinctive features of these new configurations. First of all, as we already said, we found a specific electromagnetic duality that maps solutions of family 1 into solutions of family 2. And this involves non-trivial transformation of the phi A Opoulos parameters. There is the component of the embedding tensor encoding the gauging information of the theory. One other important thing that we were able to recover some known cases for specific values of the interpolating parameter, of the new parameter. For example, if we restrict to specific values of the new parameter, we found the well-known solution of the Duff-Liu supergravity black hole solutions. While if we restrict to the nu equal infinity supersymmetric solution, we were able to recover the BPS solution, the well-known BPS solution of Cacciatori clamp. So this is a general model that has as a particular subsets that are already known cases. It's a generalization of the other cases already known in the literature. Then for other specific values of the new parameter, of the interpolation parameter, we can embed our n equal 2 model into the gauged maximal n equal 8 supergravity theory. And some of these solutions are new example of the maximal supergravity theory. And this is a very cool result, because we have new solution in the maximal theory that can be also uplifted to the 11-dimensional supergravity theory. And finally, in some sense, this uplift can also lead to new interpretation of this solution in terms of M2 brains or D2 brains that has a regular and well-defined supersymmetric limit. I think the time is gone, so thank you very much for listening.
Thank you, Antonio. So we have no questions in the chat. So, but maybe you could mention something about, let me see, since you are establishing, doing this uplifting to the deep brains
yes.
things, is there any chance that these the thermodynamic properties of these solutions could be interpreted from a microscopic point of view?
Yes, the idea is that there are some chances to do exactly this. We were able to perform a systematic embedding for specific values of the new parameter of our model into the maximal model, and then using the standard techniques that from the maximal supergravities allow the uplift to the 11-dimensional theory. It should be possible to use in the next future this computation to perform a systematic microscopic counting of the entropy and other thermodynamical relevant quantities. This is the idea.
So in that sense, I'm not updated on these aspects. So is it possible to do those calculations for non-extremal black holes? Because
yes,
as I know,
yes, it should be also possible. We know that there should be a map between the supersymmetric extremal black holes solution to the weak coupling regime of superstring theory. There may be also a corresponding map for non-extremal solution, but I'm not sure that this would be possible in the very next future.
Okay. Okay, then. So thanks again for your talk.
Thank you very much.
Let's continue. And so our next speaker is Anna Bokulic. So Anna, are you there?
Yeah, I am.
Okay. So feel free to start whenever you are ready.
Hello, dear colleagues. We will discuss the Schwarzschild black hole, immersing test nonlinear electromagnetic fields. Okay, we will begin with Walt's solution, which describes a rotating black hole in a uniform magnetic field. Then our next step is its generalization, so that the effects of nonlinear electrodynamics are included. And we will be interested in nonlinear theories in which the Lagrangian density is a smooth function of two electromagnetic invariants. So the study of black hole electrodynamics has two main lines of research: astrophysical, based on observations, and theoretical. Astrophysical black holes are surrounded by accretion disks, which produce electromagnetic fields. And these fields could influence the formation of powerful jets ejected by active galactic nuclei. Also, magnetars, which are a special class of neutron stars, they possess very strong magnetic fields, which could exhibit nonlinear behavior. As for theoretical research, electromagnetic potentials and charges are integral parts of the laws of black hole thermodynamics, and also nonlinear models might regularize black hole singularities. In order to explain Walt's solution, first we have to prove that Killing vectors can be taken as gauge fields. We will denote Killing vector field by a capital K. Then, if we take dk as electromagnetic tensor F, then we see that the first source-free Maxwell's equation is immediately satisfied. To prove that the second one really is satisfied, we need the additional result, the Killing lemma. So if we are dealing with a vacuum space-time, then we know that Ricci tensor is equal to 0, and this directly translates to d star f equal to 0. So we see that Killing vectors satisfy the source-free Maxwell's equations in vacuum spacetimes. And in this case, F represents a test electromagnetic field, which means that the background metric is fixed. There is no metric back reaction due to electromagnetic field. We can neglect it. So as it was already mentioned, Walt's solution describes Kerr black hole in an asymptotically homogeneous magnetic field. And we see that the corresponding test electromagnetic field to form is constructed from two Killing vectors, stationary, denoted by K, and an axial, denoted by M. And this particular normalization is chosen so that Comer electric and magnetic charges vanish. In the presence of nonlinear fields, Maxwell's equations have to be modified accordingly. First one stays the same, but the second one can be written if we introduce two-form Z. And this two-form Z, it reflects nonlinearity as it contains derivatives of Lagrangian density with respect to these two invariants, which are denoted by F and G. And here we will be interested in two nonlinear theories. Euler-Heisenberg, which is one-loop QED correction calculated for the process of scattering of 2 photons, and Born inflow theory, which is phenomenological. Also here, it is important to notice that the first term in both Lagrangian densities is just ordinary Maxwell's term. Now we want to find an exact solution of nonlinear Maxwell's equation. First, we can ask whether is it possible to use the basic ansatz, consisting of scaling vector only, to solve them. But we see that second Maxwell's equation gives terms which do not necessarily vanish. Another idea is to take an arbitrary function psi and rescale Killing vector field and try to solve them like that. But then we see again that the second Maxwell's equation gives a nonlinear differential equation for psi, which cannot be systematically solved. So as these attempts don't seem to work, we will use perturbative approach and expand around Gual's solution. We will expand the Lagrangian density, gauge field 1 form, and to form F with respect to coupling constant lambda. The first term in the expansion of Lagrangian density is again Maxwell's term, and the next one is the first nonlinear contribution. In gauge field 1 form, V is the lowest order correction to this basic Gual's solution. Also, we will denote by this subscript 0 terms which are evaluated at 0th order of perturbative expansion. So F0 would be just equal to dk. And we can see that by this construction, first Maxwell's equation is immediately satisfied, while the second one gives master equation for correction V. And in this master equation, we introduce the effective current J. And in this effective current, appear second derivatives of Lagrangian density with respect to these electromagnetic invariants. So those two theories in which we are interested, they both Lagrangian densities don't have mixed F times G term. And because of this, derivative with respect to both invariants vanishes. And this makes our master equation simpler. Now, it is also important to discuss when can we use this approximation scheme. Our approximation will be valid if the electromagnetic field is strong enough so that its nonlinearity cannot be neglected, but at the same time it has to be weak enough so that test field approximation is not violated. Now we can estimate and compare the orders of magnitude of left and right side of Einstein's equation. For a characteristic gravitational length scale, it is sensible to choose Schwarzschild radius. And this approximation will be valid if gravitational scale is much larger than the matter scale, which is given by magnetic field energy density. And this inequation is fulfilled even for strongest magnetic fields, as long as the black hole mass does not exceed 10 to the 4th solar masses. So electromagnetic field exhibits nonlinear behavior, but it allows test field approximation. Now we will explicitly calculate V, which was the correction to the gauge field 1 form for Schwarzschild black hole. And this spacetime is static, it is spherically symmetric, and it is vacuum solution of Einstein's equation. We will take a linear combination of two Killing vectors and calculate the corresponding invariants F and G. We can set this constant alpha to 0 because it is proportional to angular momentum in Gual's solution. And here we are dealing with a static spacetime. And now using appropriate ansatz, which respects the symmetries of the problem, we were able to solve this master equation for V. Now, another way to obtain the correction is by looking at perturbative expansion of magnetic scalar potential. We can define nonlinear H field in an analogy with the magnetic field B. And now for symmetry inheriting fields, H is the closed form, and then we can introduce scalar magnetic potential. Then we expand that potential with respect to coupling constant. From Wall's solution, we know the form of this psi 0, and then we can insert it into Maxwell's equation. And again, using appropriate ansatz, we can find the correction psi 1. And then it can be checked that it really is in agreement with previously obtained correction V. Our solution should fulfill two conditions. First, it should represent asymptotically homogeneous magnetic field. And we can check that by looking at the behavior of F at spatial infinity. And then after taking the limits, we can see that it asymptotically behaves as F0. And F0 has the same form as F for homogeneous magnetic field in Minkowski spacetime. As Schwarzschild spacetime is asymptotically flat, we can conclude that it really represents asymptotically homogeneous magnetic field. And also because of all this, we can choose normalization of V to be the same as it was in Wall's solution. Another condition that our solution should fulfill is that the electric and magnetic charge remain equal to 0. And we can check that by defining Kummer integrals for electric and magnetic charge in nonlinear case. And then upon inspecting the terms which appear in them, we conclude that electric and magnetic charge both stay 0 at lambda order. Then we can take a look at the correction to the electromagnetic invariant F, as it is observer-independent quantity. It can be decomposed as F0 plus delta F, where delta F is of order lambda. Now, in order to put all the prefactors aside, we introduce F1 in delta F. Then, after explicit calculation, it can be shown that F1 has a local maxima. And the question is whether could that have some implications for trajectories of charged particles. These two pictures show contour plots in r theta plane. M is chosen to be equal to 1, and black hole horizon is represented by the black circle in the middle. On the left side, we have a contour plot of F1, and on the right, we have a contour plot of relative correction, ratio of F1 and F0 multiplied by a constant. Now, the application of this procedure to other spacetimes is the most important question that remained unanswered. Instead of static black hole, we could study rotating Kerr black hole. But here we have a problem. So invariants F and G have complicated forms due to the form of the metric, and consequently current J, which enters master equation, also becomes complicated. So finding the right ansatz is not so simple. Also, we could look into a problem of spherically symmetric, highly conducting star immersed in nonlinear fields. Here, we need a few technical assumptions. First, derivative of Lagrangian density with respect to invariant F has to be finite at the boundary. Also, the norm of scaling vector should be continuous. And we have to assume that the magnetic field inside the star vanishes. Then we can define this boundary condition stated here. And then we get linear non-homogeneous partial differential equation for potential. But here we face another problem. Its solution is an infinite series, which makes it practically impossible to impose this boundary condition. So investigation of these two problems is left for further research. And thank you for your attention.
Thank you, Anna, for your talk. So there are no questions, but I think I missed a small part of your explanation. When you decided to consider an approximation, a perturbative approach, was it due because the exact solution was impossible to find, or simply because it was, there is no reasonable ansatz to propose to generalize Gual's method, or is simply because it was convenient or reasonable to study only perturbations?
Well, we couldn't find an exact solution, and that's why we resorted to this perturbation scheme.
Okay.
We tried those two ideas that I mentioned, so rescaled Killing vector field and basic walls ansatz, and they didn't work. Whether is it possible to think of something else, I'm not sure.
Okay. Thank you.
Thank you.
So there are no other questions. So thank you again for your participation. Okay. So I think it's time to move to our last speaker, who is Apurva Otsa. Apurva, are you there?
Yes, hello, can you hear me?
Yes, we can hear you, see you, your slides.
Right, yeah, so thank you very much for inviting me here for this conference on the universe. Now, the funny thing is that I am probably the ugly duckling or black swan in the group, that I don't work on high energy astrophysics or relativity. I'm actually a planetary astrophysicist. And I thought that this could be an avenue for some kind of multidisciplinary collaboration between two seemingly disparate fields. So I hope as a final talk, it might be somewhat interesting and something that perhaps some of you could work on at some point in your career if you wish to jump out of the black hole and high energy astrophysics paradigm. Right, so also I should say that previously I was at the University of Bern, which in Switzerland is very, let's say, popping in the field of exoplanets. And so that's why the link is here. It's easier for me to make this link. Okay, so yeah, searching for an avenue for collaboration between planetary and high energy astrophysics. So now, many might think that this is more like science fiction. For example, in Kip Thorne's Interstellar, Miller's planet, the closest planet to this black hole, is a Kerr-type rotating supermassive black hole, probably of order 1 million to billion stellar masses. There's even a paper published on this. When you look on the archive, you find very interesting scientific rigorous calculations of said scientific fiction. And on the right-hand side here, you can see a tidal bore. This is that, well, let's say I won't give away what happens in the film, but let's just say that what occurs on this planet, which you could guess, is a giant tidal wave on the order of a mountain, 1 to 10 kilometers. This can be easily calculated by just taking the ratio of the tidal potential and the acceleration due to gravity. And it's actually a question I asked on my final exam for the students studying planet formation and evolution, only because it can be found analytically. Now, in our field of exoplanetary science, we're actually working on a model with a few people that are here in the audience, also trying to maybe explore a seemingly disparate field that a tidal bore can indeed be observed. It's a project we have in prep, and we find that the tidal bore is even higher, something on the order of 50 to 100 kilometers. And this can exist on a molten exoplanet. So it's not water, not liquid water, but it's a melted mantle material, which is probably either sulfur dioxide, silicon oxide, magnesium, any kind of metal. And just to make the link right now, metallicity for any extragalactic astronomers in the audience could also be a feasible link to planets, which are of course simply dust for many. So that's an ongoing project. But there are no observed planets around black holes yet. I cannot think of too many observables at present. I think there have been theories of how tidal interactions can strip a planet and you can see the radiation, but it's more relevant for stars, I think. But there have been observed planets around neutron stars, the next, let's say, dense thing in the universe. And the Schwarzschild radii are around 4 kilometers. And this is the planetary system, 1257 plus 12. We always have these fancy phone numbers here. Now, just to return to exoplanet astronomy, it's very, very biased, and there's 4,000, more than 4,000 exoplanets that are of very diverse densities, masses, and radii, and chemical composition. But the pulsar planets in our galaxy, there's only 9 of them, and perhaps 12 if confirmed, which is very small. This number has thought to be either because of a observational bias or because of possibly just the formation of pulsar planets themselves, which we will touch. And just to refer to the next thing after these thousands of planets, maybe exomoons. So a lot of my work focuses on those small things that you cannot see that light up in methods that may be common but are not looking for these objects. So right now there are no confirmed exomoons, but perhaps 20 candidate exomoons, probably 19 or 18 of which were only speculated or announced in 2018. So it's a booming field at present. So let's see. Well, with all 20 exomoons booming, right? Yeah. Okay, so Arecibo Radio Telescope. This is an actual poster that was made by Arecibo Observatory. As you may know, it collapsed in 2020 in December. Very, very tragic year. And the interesting thing is that these posters really capture the essence of the physics that we can study here. There is almost, a plethora of possibilities of what could be occurring. And these planets are zombies. They're back from the dead because there was a supernova. And how could a planet form around in a supernova-like environment? And so there are a couple of theories there that they could be second-generation planets where they formed in the remnant supernova and the fallback dusty accretion that could be occurring. But the more popular idea is recently by 2 guys from Columbia University in New York, where they think it's evidence that there was a binary, a white dwarf star, and they underwent Roche-Lobe overflow. And so that gas formed this accretion disk, which we can see here. And in that accretion disk, these planets formed. And the titles of these pulsar planet papers are actually quite interesting, that some of them discuss 10 to the 29th power carat diamonds. And I think this is the calculation that the density of this disk would be extremely high. The density of the grains, it would not, because most other, let's say the lighter elements would have long evaporated and would not create something like Jupiter or even Earth around these zombie worlds. I showed this this table so you can see the sizes of the planets, and you can see that the very first confirmed exoplanet was a size of a super Earth. Now this would predate the radial velocity or transit method by a decade or two. And what is even more fascinating is the closest planet is the size of our moon. And this, and you can just count the number of papers if transiting radial velocity, but the precision of millisecond pulsars is unparalleled. And I think that is extremely helpful in discerning the precise environment of these planets, because they are not, their radii, or at least their masses, are not uncertain to tenths. Sorry, I did not include the uncertainties, but it's roughly 0.00 or 0.01 Earth masses. And once again, this is also a new field for me. I am simply jumping in here to see what can be achieved with a journal such as Universe in the planetary context. Okay, so to keep things even more exciting, it's like a pulsing discotheque at this pulsar. This is an animation by Unser Kosmos. It's on Wikipedia, actually. Everyone can download it free range. And these are discotheques that are obviously dangerous. If you're on these planets, there will be two mechanisms. You can have relativistic ion winds, which have equivalent temperatures of 10 trillion Kelvin. This can be calculated in another way if you look at the photon energies as giga electron volts. I think even discussion of tera electron volts. And then, of course, high energy X-ray radiation. Now, high energy X-rays have actually been observed at this star, at this pulsar. And so there are tight constraints on how many X-rays, the pocket of photons that come in, how much of that flux can be observed, and how much of that will then bounce back any primordial atmospheres. And this is very similar to what we do at exoplanets. We've studied these mechanisms at close-in exomoons, and which seem to be degenerate also with exoplanet transmission spectra. So we have degeneracies in our field, and so it could be that these numbers that are calculated also have other mechanisms that are waiting to be explored by other scientists. I had to put up the NASA Exoplanet Travel Bureau poster here. They, where the nightlife never ends. This is a very interesting rogue planet, but I always think where the nightlife never ends is more like this this pulsar system. But anyways, the Patruno and Kama did a very interesting calculation where they show that when you do plot the luminosity versus the orbital distance, there's something like a neutron star habitable zone. For the life of me, I cannot imagine what kind of life that would be. I honestly don't think about life around neutron stars, but it does show that there is a range here between an X-ray assumption and the total luminosity heating that drives the pulsar wind. And so there's a lot of 1, 2, 3, 4, 5 orders of magnitude range that is left to be explored by theorists, so that there may be an observable, or at least the fantasy of having a habitable zone around a pulsar can be at least imagined in a different way. But it's interesting. Now, the physics that we use at exoplanets are motivated by moons in our solar system, which is, I think, a big advantage of planetary science is we can observe things with spacecraft around the planet. Many of you might be aware of the mission Juno, which is currently in orbit around Jupiter, or Cassini that was at Saturn. These instruments are equipped with plasma spectrometers, which can constrain ions, which will then constrain the three main atmospheric escape mechanisms displayed here. And the model is called DISHUM. It's just a very simple semi-analytic model where you calculate the interior heating, either due to tidal dissipation or due to radiogenic heating, and then you calculate what shoots out of the planet, and then you calculate what shoots into space, which are all luckily observables at stars. So surface atmospheric escape, just a brief overview. By the way, how am I doing on time? Do I have 10 minutes or?
Yes, I think you have already, yes, 10 more minutes.
Good, good.
Yes.
I just was wondering how much detail I should go into here. So surface-driven escape is an escape mechanism. And when I say escape for these bodies, I refer to volatiles in general. So it could refer to actual atoms or molecules on the surface of these planets, which are also being ejected into space, which we will see. So it requires a source from the surface, which is constrained by m.0. Now, m.0 is the sublimation rate of the planet, which is then constrained by the Jeans parameter, or the Jeans escape parameter, which is simply a ratio between the gravitational energy and the thermal energy. This is generally important for, we can say, planets which have a high Jeans parameter above 100. And these planets are actually very cold or not hot enough. So the Jeans escape mechanism is negligible. And the upper atmospheric escape is actually a ratio between the heating due to the X-ray photons, as the previous authors described, and just the binding energy. Also very simple, but what we don't know, as you saw in the previous plot, is how efficient is this X-ray heating. And once again, Patruno and Kama do a very good job of showing how far the constraints can go. Now, plasma-driven escape is a, let's say, maybe more relevant for discotheque, or something that is pulsating and has a magnetic field strength of 100 million Gauss to a billion Gauss. And this is, I just want to point out, this is far 7 to 8 orders of magnitude larger than Jupiter. Of course, the distances are different, but the scaling as 1 over r cubed will result in a drop-off of 1 over r to the 6th, but it's still severe, which we will see. Just to return to the physics here, the expression can be derived, and this is, by the way, I didn't cite, it's just in my atmospheric evolution book, Lit, which we used for the course in Bern, planet formation and evolution. And the plasma-driven escape is just a scaling law to Io, because plasma-driven escape, as far as I am aware, has only been directly measured at Jupiter's moon Io. It's possible that at Venus, of course, the Earth and Mars, we do have plasma-driven escape, but it's also, it's not necessarily ram pressure-driven or magnetic pressure-driven. Those are the two main mechanisms we study here. Those processes might be more shaped by charge exchange, which are important plasma reactions as well. So simply you can scale to Io by scaling the ratio of the plasma pressures and the ratio of the ion velocities, the ratio of the binding energies, and then the exobase altitudes. The exobase is that altitude at which an incoming plasma, would most likely start impacting the atmosphere below and result in atmospheric sputtering, where momentum transfer occurs and the atmosphere starts escaping. The exobase altitude is the difference between the troposphere and the tenuous part of the atmosphere, the collisional part of the atmosphere and the collisionless. So that was just a quick overview of that. And here I can show you a nice observation. This is in the sodium filter on top, and this on the bottom is plasma. This is Jupiter's plasma gyrating, since its magnetic field rotates faster than its rotation rate, and it is also tilted to the rotational equator. And what we see are giant clouds of ions. These are the kind of simulations I think we could actually make progress in this decade. It would take a long time, I think, sort of PhD projects. But the idea of this is to really see, from things we know in the solar system, how could it occur around another extremely magnetic object? Jupiter, of course, is the most magnetically powerful object in the solar system, and the only place where we have such data of that at Jupiter and Saturn. And Saturn's field is much weaker, so I focus on Jupiter. And so using this data, we have more observational constraints. For example, we can see that even if you're far from the pulsar, if we can now make that analogy, if you're far from the pulsar, 1,000, say, pulsar radii away, well, of course, the pulsar is only 10 kilometers in radii, but farther out, you can have a giant cloud which can be observed. What you are seeing is atomic sodium luminescing, fluorescing, due to the emission of the sodium D lines. And so here I'm not saying we should look for sodium at pulsars. Well, if anyone thinks of a way we can do that without transmission, that would be a good idea. But I'm suggesting that there might be giant clouds of some material that is escaping from these planets, which we can observe at a much lower frequency, perhaps. And the critical result is that, at least for the first planet, I calculate and confirm the results of the previous authors, that the planets are evaporating 1 billion kilograms a second. Now this is extremely large, and to give a scale, Io, the most geologically active body in the solar system, is shooting out 1,000 kilograms a second. And that is magnanimous. So we are talking 6 orders of magnitude larger. This also occurs, this is 3 orders of magnitude larger than at close-in exoplanets, at least in the sodium, perhaps comparable in the full volatile ejection and escape. And this implies that the evaporation rate of the entire planet is less than 3 million years. Now, this is assuming that the surface is also being heated and evaporating slowly. So, of course, analysis should be done to check the sublimation curves of the surfaces. But this is some back of the envelope results to ignite some kind of analysis in the future. And so the surfaces must be generating these tertiary atmospheres, which roughly 1 giga electron volt may be able to generate atmospheres 1,000 times as thick as Ganymede, where the column density is 10 to the 15 particles, 10 to the 14 particles per centimeter squared. And so I say a chance to detect these 10 to the 29 carat diamonds, because once again, as we said, these planets have very bizarre compositions. And it's an opportunity to study planets of very different composition than we're used to, even in the exoplanet field, where we get headlines of carbon planets and diamond planets. I think these are possibly more practical in that sense of assessing that. Right, and then lastly, I just like to say that there are ongoing campaigns at transiting exoplanets. So the first 3 are the instruments we've been using. high-res spectrograph on the Keck telescope, operated by Caltech and others, and the espresso spectrograph, a very high resolution and stable spectrograph on the Very Large Telescope in Chile. Had to observe last Wednesday where there was so much wind that we almost had to cancel mid-transit, and we had to switch to a backup target within a scale of minutes. But over that, and now to highlight an ongoing campaign with the Giant Meter Radio Telescope in Pune, India. This is a collaboration with TIFR and the Indian Institute of Astrophysics to detect possible presence of a plasma torus by a cyclotron maser mission. And these are the kind of physical processes I think we should look for at pulsar planets, because they would at least be able to constrain perhaps the magnetic field, or at least the magnetic environment of what is occurring. And of course, maybe the precise frequency should be worked out, but I hope, yeah, this is something that could be pursued and thought about. And lastly, I'd just like to say this is inspired and reminiscent of Peter Goldreich and Lyndon Bell from 1969, that far before they even knew Io was volcanic. So analogously, far before we know any of these planets are active around these pulsars, there were these radio bursts that are occurring due to Io's volcanism interacting with the plasma torus. So yeah, with that, I think I conclude, and I'll take any questions.
Okay, thank you, Apurva, for your nice talk. It's a really interesting topic, of which I know nothing. So I don't see any questions here from the audience. But I'm very curious about this topic. So I have a question regarding these second generation planets after the explosion of a star.
Right.
Because the mechanisms of formation must be completely different, because the wind disperses all the light elements and you only have heavy elements, and the radiation from the pulsar is huge, so it gets rid of everything. So do you have an estimate of the masses, the minimum or maximum masses of these second generation planets?
Well, the masses are actually known, like they're roughly 4 and what's that, and roughly moon masses. So but the total mass of this second generation planet, I think, is unknown, but I think the idea is that they're extremely high density, and that is what constrains it. But that's a good question. I would be curious to work with planet formation experts that might have a minimum mass of that pulsar nebula, I guess, right?
Yeah, I see. Okay, so we have one question here. Someone, Arun Kumar Bisham, is asking if there are any prospects of detecting life on these exoplanets.
Gonzalo, I have also some points, some questions.
Okay. But right. Before your turn, Lorenzo, let's see if Apurva can answer this question.
Yeah.
In the chat.
So yeah, the habitability is something that was, sorry, I think I breezed past it. The habitability and the prospect for life around these exoplanets, I think, was calculated by Dr. Petruno and Kama. And here you can see that if the luminosity is just right and the orbital distance is just right, you can get that Goldilocks zone. And I suppose this is nice, but one interesting project or question we can ask is, what about this high energy radiation? What will it do to the surface? Will the idea by Petruno and Kama is that it can remain habitable because you have thick atmospheres, and the thick atmospheres can protect from high energy radiation. However, as we just had the critical result, the primordial atmospheres would evaporate quite quickly. So I think you would build much more tenuous atmospheres. So it's an interesting question, but I'd have to first think about Ganymede and others before, yeah. But thank you for that.
Okay, so Lorenzo?
Okay, actually, some comments. First of all, with such a mass loss ratio, it's very, very high. There are also important orbital effects because the planet goes away from the main star. I had a paper on that some years ago on new astronomy when I calculated the variations of the orbital elements, in particular semi-major axis and the eccentricity on the orbit of a planet which undergoes mass loss. Then another point, in these exoplanets, it is interesting that general relativity may have a direct impact on habitability because of the spin precessions. I mean, the Sitter precession and the Schiff precessions, those measured by gravity probe B. Because if you have a planet very close to its main star, the spin of the planet undergoes such precessions, the Sitter and Schiff precessions. Mm-hmm. So also the obliquity of the planet changes in time, because the obliquity is the angle between the orbital angular momentum and the planet's spin angular momentum. Mm-hmm. And general relativity impacts both of them. And you know that the obliquity is a key parameter for the habitability of a world, of a planet, because it controls the radiation from the main sequence star orbited by the planet. And general relativity may have an important impact because it can induce variations tens of degrees over time scales of some millions of years. I have just put a couple of preprints on archive, and also on exomoons, because you can have such effect. On the planets orbiting M dwarfs, they have orbital periods 4 days of 4 days. And also on exomoons, if you have a main sequence star, a Jupiter at 1 astronomical unit, and an exomoon, the spin of exomoon, of the supposedly habitable exomoon, can be shifted by general relativity with respect to the ecliptic plane. And about the supermassive black holes, recently there is a research group from Japan which has shown that a lot of planets, of rocky planets, potentially habitable planets, can form around supermassive black holes, just outside the accretion disk. They called such planets planets with the B, planets, black hole planets, which can be habitable, getting the energy output from the accretion disk. And also in that case, the de Sitter and the Schiff general relativistic spin precessions may have a strong impact because they tilt the planet's spin axis, changing the obliquity in a very relevant way. But also the planets, the potentially habitable planets around the neutron stars, I think that they should undergo this effect.
Mm-hmm. Those are extremely insightful comments. Thank you, Lorenzo. This is the kind of synergy I was looking for. I never thought of the de Sitter shifts, but now that you mention it, that is something that I meant to investigate. I meant to investigate the GR effects on said planets. And I think, right, if you have references, you can point me to, we can chat offline, and that would be good. And the other thing I was going to mention was obliquity tides and tidal forces are extremely important for Neptune's moon Triton, as it's like precessing inside. And so combined with the general relativity of a neutron star, I'm sure that has severe implications on habitability, if not the fate of the exomoon or the pulsar planets themselves.
Because in that graph, you shown that the habitable zone of the pulsar, around the, yes. And I see that the habitable zone starts even at 0.001 astronomical units. So very close to an object which has the mass of the sun, or even larger, of course, and an angular momentum larger than that of the sun. So I can imagine that the general relativistic effects are very strong on such potentially habitable planets, because they can stay very close to the pulsar. That's interesting, because, you know, general relativity displays the orbital plane by means the length theory precessions, and also the spin of the planet. And the obliquity is the angle between these two vectors, the orbital angular momentum and the spin planet. So I can imagine that such effect should be very, very large. Quite interesting, this field.
Yeah. I suppose theoretically, if the planets, after you form a simulation where you show the formation, it should be investigated what really occurs here, and perhaps then you can just constrain this graph and say, well, actually, if it's too close, and you have to come to a certain distance from the black hole or the neutron star. So yeah, we should investigate that further. Thank you again. Yeah.
Okay, thank you, Apurva. And so we are at the end of the conference, of this session today. So I would like to thank all the speakers and all the participants for making this event possible. And Lorenzo, I don't know if you want to say some words to say goodbye.
Yes, of course. I'm grateful to you, Gonzalo, for your great work, and also to all the speakers. They delivered very interesting talks. And just an idea, a comment, Gonzalo, why don't think about such effects from modified gravity? I mean, one could think about calculating such kind of effects due to some modified models of gravity, putting some anthropic constraints.
To the orbital precessions, you mean?
Orbital and spin precessions, for example. Because think about a planet, a potentially habitable planet around a supermassive black hole. Of course, it is not so close, if I am correct.
The chances of measuring those objects are difficult observationally. So,
yes, of course.
And confronting that with GR and other theories is even more challenging. But in principle, I guess it can be done. So it's just a matter of exploring all these post-Newtonian effects in other theories. Maybe you can even use the parametrized formulation.
Because you should have, the planet should be at 1 parsec, if I remember correctly, from the supermassive black hole. So in principle, you could look at some long-range modified models of gravity, introducing some cosmological constant type effect. but it is just an idea.
Yeah, no, I will think about it. It sounds interesting.
Okay. See you.
Okay. So thank you everyone for being here, and hope you keep enjoying the meeting these days. So
Bye-bye.
Thank you. Bye.